Hello, my name is Bob Card. I'm the ESG Marketing Manager for the Americas. And today we're going to talk about the convergence of 5G, fast charging, and USB-C with programmable power supplies. So I want to first talk about smartphone charging. I know you don't probably call on suppliers that make smartphones. However, it's sort of the elephant in the room with respect to the charging market, because to a large extent, most things that need to be charged are arguably phones. So let's start there. There's over 3.5 billion smartphones in the market. In 2020-21, maybe a small percentage, 1 or 2 or 3% are 5G, but that's going to grow significantly. And 5G is a big deal. It's driving larger screens and larger batteries. And the fact that it's driving larger screens and larger batteries, coupled with the fact that a big trend for the last 5-7 years has been faster charging, just for the better user experience. What's happening is you're going to see chargers requiring more power. So the chargers for phones are going to grow from what we typically see a few years ago, 10 watts, 12 watts, 15 watts, closer to 25 watts, 35 watts, 45 watts. That's going to drive overheating of smartphones. So a smartphone, relatively speaking, is a pretty small device, right? It's not a lot of real estate. So you're putting that much power into a small space, you're going to dissipate power. So you got to be careful, right? And that's going to heat. Excessive heat's a terrible user experience. So you got to improve the efficiency if you want to do all of this. If you want to charge fast, these bigger phones that are typically going to be, you're seeing in 5G, you got to be more efficient. And one of the best options for charging efficiently, and one of the better customer value propositions, is programmable power supplies with USB-C. And that'll cool down the phone so you can go and charge as fast as you want. So and I want to point out one thing on this slide on the right-hand side is that the USB-C markets are growing. The tails are growing. There's more and more, as you see, more and more phones proliferate. And it's not just phones. It's laptops, tablets, also drones, power tools, many different things. I'm seeing more and more long-tail companies looking for a Type-C solution because you can do up to 100 watts. So it's pretty cool. So it's not just the power banks, the USB hubs, and charging basically on furniture or with furniture, but I'm also seeing it with power tools. I'm having power tool companies come to me and say, look, your carpenters out there need to have a Type-C connector nearby because their phone's an integral part of their business, right? They need to talk to people that are providing them with parts, and also their customers, and also other contractors. So they have to be communicating all the time. So if your phone dies, you really can't do any kind of business. So we're seeing it with portable tools. We're seeing it with planes, trains, automobiles. Motorcycles even. Harley Davidson reached out to us talking about having a Type-C port on their bike. Herman Miller, Steelcase, IKEA, furniture, big deal. All these long tail customers who really aren't really super fluent in USB are interested in adding that to their products. Also boats, hospital beds, hospital chairs. Lots of long tail applications, which is really great for the channel. So I want to start with talking about the #1 selling 5G phone in 2020, and I believe that's the case in 2021, and that's the Samsung Galaxy S20 series. They've just come out with the 21 recently, which is actually quite similar as far as the battery is concerned. So if you look at the specifications, we'll talk about the S20 Ultra 5G for now. It was released in March of 2020. It's got a 5,000 milliamp hour battery. It advertises charging up to 45 watts, and it supports USB Power Delivery 3.0, which I'll cover more in a moment. So if I were to take 45 watts and extrapolate that and look at sort of on the napkin, estimate the total power after some efficiency loss. So let's just say from the wall all the way to the battery itself, we got an 80% efficiency, 20% drop from the wall all the way to the cell. That's about 36 watts. So if I look at 500, this table up here in the top right, a 500 milliamp hour battery, if you want to get roughly, the typical charge rate is 0.7 C rate. That's what we've been seeing over the years, which is nothing more than the capacity times 0.7 C, which is 3.5 amps. And that'll yield about a 45-minute time to charge from zero state of charge or fully empty to 50% or half full. And that's a peak charge power of 15.2 watts, nothing more than 4.35 volts, which is the maximum battery voltage times the current. Now, if you want to get a 30-minute time to charge for 21.7 watts, that's a 1 C rate or 5 amps. And then a 1.5 C rate or 7.5 amps will yield a 22-minute time to charge from 0 to 50% stated charge. And that's roughly 32.6 watts. So that's not too far from the 36 watts that I estimated. So my sense is, I don't know exactly what's going on inside the Samsung Galaxy S20 Ultra 5G. I really don't care. But the point is, I think we're dialing into more or less this loop here of roughly 7.5 amps going into the battery, and what it's going to take to be able to provide that power. So you get that fast charge of roughly 22 minutes, 0 to 50% state of charge. Now, when you talk about all of that, again, this is a small piece of real estate, right? There's not a lot of opportunity to wick away the heat that's caused for doing that kind of charging. So you need to be efficient, right? The efficiency goes down, the heat goes up. And that's a big problem. So one of the ways to be able to make that work better is to use power delivery. So let me first talk about power delivery a little bit. On the left-hand side, you see the Type-C, USB-C without power delivery. And that's called an implicit contract. And the most you're going to get is 15 watts. That's 5 volts, 3 amps. So I'm talking two devices plug into each other with a Type-C cable. You're going to have, if they're both Type-C products, they're supposed to be able to do an implicit contract up to 15 watts and do a number of other things I don't have time to go into. But if you want to get it to the right-hand side of this vertical green dotted line, and you want to get to 100 watts, which is 20 volts, 5 amps, you need to use power delivery. So power delivery incorporates what's called an explicit contract. So if two USB PD capable devices plug into each other or with one another in a cable, they first do an implicit contract, then they're obliged to do an explicit contract if they can, up to 100 watts. And I'm going to talk a lot about that in this presentation. And then they can do that with fixed, variable, and programmable power supplies. So for USB power delivery version 2.0, you had what was called, they offered fixed PDOs, up to a maximum of 7 fixed PDOs or power data objects. An example, and that's for 100 watts. So an example would be like 5 volts, 9 volts, 15 volts, or 20 volts. Those are your typical voltages, either 3 amps or 5 amps. A little later, PD came out with 3.0, and 3.0 introduced PPS, or programmable power supplies. And what they do is they offer, instead of fixed voltages, they offer a range of voltage from 3.3 volts to 21 volts in 20 millivolt steps. So very, very fine granularity. Same for the current, up to 5 amps and 50 milliamp steps. So that finer voltage current granularity, this helps optimize the efficiency between the source TA and the sink, which could be a phone, tablet, or a laptop, or a drone, or any number of things. Power tool, any number of things. And these are screenshots right out of the specification, the PD specification for table 622 and table 10-8. So I want to now talk about sort of the framework that goes into this power contract negotiation between two PD-capable devices. On the left, I've got a PD source, and on the right, I've got a PD sink. This PD source can source up to 100 watts, 20 volts, 5 amps. And in between the two, I have a Type-C cable. And there's many pins and wires for Type-C, but I'm just highlighting 3 of them. V-bus, which is the plus for the power. Ground is the ground for the return current. And then CC is a wire that goes between the two of them that for PD and the implicit contract is a single wire protocol where messages, it's a digital interface where messages are sent back and forth between the source and the sink. And that's kind of the whole point of PD, is it has this messaging back and forth. It's a much more robust and sophisticated link and connection between a source and a sink. Again, sources provide power, sinks consume power. Typically, your sink would have a battery and you're charging it. That's not always the case with USB. You can have what's called a dual role power, where either one can have a battery or be a source. They can be both sources and sinks. But to keep it simple right now, let's just talk about a PD source on the left and a PD sink on the right. Now, that cable can go up to 5 amps. But if it goes over 3 amps, per the laws of USB Type-C, you have to have an E marker, which is an electrically marked cable. It's a piece of silicon that sits in the connector of the cable on the little paddle board. And what that's there for is to tell the source if it's able to handle more than 3 amps. So if it's a 5 amp cable, you need to have an E marker. And that's for safety, which is a good thing. So the very first thing that happens is that when you plug them in together, is the source does a discover identity on the cable, on the E marker, to see if it's 5 amp capable. And that's done with a starter packet prime. The starter packet prime is sort of like a header that tells the sink to ignore it and the E marker to listen and respond to it. So if the E marker is not there, it's a 3 amp cable, then there won't be any, he won't get a good CRC back from the E marker. If it is there, he'll get some information. They'll have a little chit chat, and then the source learns if it has a 5 amp cable or not. So the next thing it does is it advertises its source voltage and current capabilities, and that's with an SOP as opposed to an SOP prime. SOP means the sink needs to decode it, and the E marker needs to ignore it. So that way you don't have collisions. So it advertises up to 7 power data objects, or PDOs. And it's sort of like going to a restaurant and sitting down and receiving a menu from the waiter or waitress. Very similar. You get your menu. In a similar way, the sink receives these source advertising capabilities. Then the sink looks through them and says, well, I'm going to request one of them. Sends that back to the source. The source looks at it and says, okay, I'm going to accept that, sends an accept message. And the sink sees that, sends back a good CRC. And then once the source sees the good CRC, which tells the source that the message got there okay, then it says it's going to put out an agreed upon power message, and that's going to be the PD power contract. And that's basically it. It's like going to a restaurant and ordering food. But it's a really good, safe, robust way for a source and a sink to sort of, talk to one another to make the most efficient and best use of either the power provision or sourcing and the power consumption. Okay, so let's talk about, so what I'm going to do is show you a real life example of a power contract. But first I want to introduce our reference design. And this is the FUSB 3307 and the NCV 81599. So basically, starting on the left, we've got an input voltage, and this board accepts anything from 4.5 volts to 32 volt input. And you can see the NCV 81599. It's a classic buck boost controller, because you can see the external inductor here and the 4 FETs on either side. 2 sets, high side, low side on the left, high side, low side on the right. And that basically puts out a 5 volt to 20 volt rail on the Type-C connector. Now you'll see that the 81599, the I2C is tied off. So there's no adjacent MCU. What you do see is that the comp input, which is the analog input that controls the buck boost, that's being driven by the cath output of the FUSB 3307. And so basically the 3307 controls, it has the 2 CC pins and the D plus and D minus. It controls this Type-C connector here, as you can see. And it also has built in a state machine that is compliant to PD 2.0 for fixed PDOs or PD 3.0 for programmable power supplies. Up to 100 watts, state machine based. So it's very cool. You don't have to write any firmware. You don't have to do any configuration. Basically, it just takes over the buck boost, and based on the power contract that we discussed earlier, it puts out the voltages and currents per the negotiated contract. And it's also tamper proof because there's no firmware. So nobody can go in and muck with it. So it's tamper proof, which is another benefit. So this reference design, you can also use it in an AC to DC environment. So that cath output, instead of that controlling the buck boost, it can control an opto, which then feeds back to a primary side controller here, and that controls that in combination with a secondary controller with the isolation you see here. You can have a full-blown AC to DC solution as well. So a very flexible and robust device, this 3307. One of my favorite devices, it's really the crux of this presentation, is this device with the buck boost. So this is what the board looks like. You can see it's a 1.75 inch by 2.94 inch board. The 100 watt version is 30.9 watts per cubic inch, so ultra high density. Here's the Type-C connector. Here's the FUSB 3307. And here's the buck boost with the 4 FETs here, and then the conductor. And so, with this, you can. What's nice about external FETs and having a controller is you can control the heat a little better. You can control the power a little better by sizing these FETs accordingly. And we also have all the protections you would need: OVP, OCP, undervoltage, overtemp as well. It's self-powered off the input. State machine driven, no MCU, tamper proof, I mentioned that, and it's fully compliant for programmable power supplies. So one thing I want to touch on is the efficiency of the buck boost. So with a 12 volt in, you can see that the output efficiency for voltages from 9 volts to 20 volts exceed 97% efficiency at 3 amps, which is world class. And also is 95% efficient for a 5 volt out. You'll also notice at 1 amp that all the voltages are above 90% efficiency. In fact, the 5 volts above right at 90, but the other voltages are closer to 95 to 96%. So a very efficient solution, which is important for controlling the heat and minimizing the power dissipation. So first, we're going to look at a PD 2.0 power contract example, a real-world example of this. So I took a MacBook, which, by the way, uses Type-C, which isn't too shabby because, Apple's big on the Lightning connector. However, for all their MacBooks, they use USB-C. For all their phones, they stuck with the Lightning connector. However, they do use power delivery for the protocol. So that's worth noting. So I'm going to take this. This is my sink. I have a 5 amp cable labeled here. And then I have one of that board that I described, my 3307 81599 demo board, which you can order online. I should have said that. Right here is the link for ordering that board. And I have a 20 volt brick power supply there, pretty simple. And in between the source and the sink, I put a total phase sniffer. And the total phase sniffer basically is a PD sniffer. It sniffs out all the PD messages, which I'll go through that in detail. And then it also captures the voltage and current at this point. So you can see what's going on, which is very cool. So the very first thing that happens after I plug it in is that the 3307, which is my board, will do a discover identity command or message. You can see right here, discover identity, with an SOP prime. So that SOP prime, as you remember, the E-marker decodes it and the sync ignores it. So the MacBook doesn't even look at it. And what happens then is the cable, you get a good CRC back from the cable responds to the good CRC saying it received that discover identity command. And then the E-marker puts out a list what it has. So it responds with a vendor ID of CE Link Limited, as you can see here, the vendor ID, VID. The cable type is passive, and all that means is it doesn't have redrivers in there to compensate for the cable loss of the super speed lines. And it's 5 amp capable, so that's cool. So now my board knows it's connected to a 5 amp capable. So when it advertises its voltage and current, it can go to 5 amps. And so there's a good CRC that tells the 3307. Let's see. It does an SOP prime back to the E-marker to say it received that information. Now the 3307 puts out an SOP, so now the E-marker ignores it, and the sync decodes it. And here are the 7 power data objects. So the first 1, 2, 3, 4, the first 4 are fixed, and the last 3 are augmented. When you see augmented, that's PPS, programmable power supplies. So you see the first fixed is 5 volts, 5 amps. And remember, this is a 60 watt power supply. I should have mentioned that. This is a 60 watt power supply. And it puts out 5 amps, 5 volts, 9 volts, 5 amps, 15 volts, 4 amps, 20 volts, 3 amps, and then these 3 augmented, which are 5, 4, and 3 amps respectively, 3.3 volts 12 to 12 volts, 3.3 volts to 16 volts, and 3.3 volts to 21 volts. So it's going to the, you get a menu, get different things you can order. You can get a grilled cheese, you can get a steak and onions, or you can get the prime rib. So the MacBook responds with a good CRC, and then the MacBook does a request, and it requests position 4. Well, position 4, 1, 2, 3, 4, is the last fixed PDO, which is 20 volts, 3 amps. Okay. But it's also going to say, look, I don't need the full 3 amps, so I'm just going to take 1.5. So that's good. So my board knows I don't have to give it the full 3 amps. So that's part of the intelligence built into this whole specification, which I think is great. So you get the next thing is a good CRC. The 3307 responds with a good CRC back to the MacBook. That tells the MacBook that my board received its request. So that's all good handshaking, right? That helps the robustness of the interface. So then my board sends 3307 sends an accept. And then there's a good CRC back from the MacBook. And then my board sends a PS ready, and then a good CRC back from the MacBook. And now we're off and running. We've got a power contract, and things start. And so this is the IV on the x-axis is time. This is roughly the first 2 minutes of what we just looked at. On the left-hand side, vertical axis is voltage in red, from 5 volts to 20 volts. And on the right-hand side is the current in blue. And you can see that originally it started off with 5 volts, right? It did that position 4, just wanted 5 volts. Then it went to the augmented, and it said, I want to go to 20 volts. And sure enough, that's what it did. The red went to 20 volts. And you can see the blue current started, sort of ramping up over time, a little bit of time. And now it's consistently charging at roughly an average of 1.3 amps. And it's doing what it said, right? It's staying under 1.4 amps. And it said I would draw no more than 1.5 max. So it's doing what it said it did. And so it's a very well-behaved, scenario now. Everybody, both the source and sync know exactly what's happening, and they know what to expect. And I just want to point out, so I terminated the data gathering here after about 2 minutes, but I can just tell you that it continues going this way for quite a while. And you can see at 20 volts, 1.4 amps, that's roughly 28 watts of power that's drawing from my board. So now let's look at another example. This is with PD 3.0, which introduces programmable power supplies. So what I'm going to do is I'm going to replace the MacBook with the Samsung S20 Ultra 5G phone, the #1 selling 5G phone on the market. And I'm also going to replace my board with this 25 watt Samsung travel adapter. So that travel adapter is a 25 watt travel adapter. And I've still got the sniffer in here. And this sort of gives me a bit of a baseline to find out what Samsung's up to, all right? What's the #1 5G phone up to when it's using PPS? What is it doing? Let's look. So the very first thing is that the travel adapter does not look for a 5 amp cable because its max current is 3 amps. So there's no point in asking. It doesn't care if there's a 5 amp cable. So there's no point in wasting time talking to an e-market because it's not going to go over 3 amps. So the first thing it does is it advertises its source capabilities. In this case, it advertises 4 objects, 2 fixed and 2 augmented. The 2 fixed are 5 and 3 amps, 5 volts, 3 amps, then 9 volts, 2.77 amps. Again, it's a 25 watt travel adapter. The next 2 are 5.9 at 3 amps, which is 17.7 watts, and then 11 volts at 2.75 amps, or just over 30 watts. So then it does, so what happens is the S20 requests position 1, or 5 volts, 3 amps from the travel adapter, which is basically 9 watts. Or 15 watts, sorry. And then about 14 seconds, so it does this thing, and about 14 seconds later, oddly enough, out of nowhere, from my perspective, it changes its mind and requests position 4, which position 4 is the PPS augmented 3.3 volts to 11 volts with a max of 2.75 amps. And oddly enough, and then it requests 8 volts and 2.75 amps. So it's within the range. 8 volts is well within the range of 3.3 to 11. And then about 575 milliseconds later, it bumps that up to 8.04 amps. Sorry, 8.04 volts. So it increases 40 millivolts. And then it does that again about 200 milliseconds later. And then another 200 milliseconds later, it does it again. So it keeps incrementing every 200 milliseconds. It keeps incrementing the amount of voltage it wants from the travel adapter. And so I've captured in here in yellow, basically what I captured here. And you can see it went to 5 volts and then jumped up to 8 volts and then started ramping up that 8 volts. And again, red is voltage, blue is current. And you can see at the same time, it's stepping up its current to, maybe 1.6 amps here. And then about, I've got time here. So it's about a little in between 1.5 to 2, a little over 2 minutes. It starts ramping up the current pretty high. And it goes all the way up to, just around 2.7 amps. And out of nowhere, and I see a command or a message I've never seen before, and that's an alert coming from the travel adapter. So the travel adapter issues an alert to the S20 because the S20 is syncing the maximum current. How cool is that? So now, the phone, they're talking to each other. The phone says, hey, I want to take a max of 2.75 amps. And then the TA says, okay, I'll give it to you. And then when it reaches 2.75, it sends an alert saying, you've hit your limit. So if I zoom into that alert, which happens right here, I'll look at the commands that are before and after that alert. Before the alert, it's up to 8.96 volts for requesting voltage, and the current's at 2.75 amps. And then the travel adapter asserts the alert. The phone recognizes that and then sends a get status back to the travel adapter. The travel adapter receives that and sends a status where it tells the phone that the travel adapter's temperature is 4 degrees Celsius inside the travel adapter. And then the phone sees that and then bumps up the voltage to 9.06 volts. Again, it does that 40 millivolt increase, keeping the current the same. So that's kind of cool. And then it keeps going and basically time passes. And what it does is it starts dropping the current a little bit. And then it raises the voltage a little bit. And you can see the peak power right about here I captured is 9 volts at 2.75 amps or 25.75 watts. So that's about right, just under 25 volts. So that's cool. That's an example of a PD 3.0 example. And now what we're going to do is look at another PD 3.0 example. However, we're going to replace the travel adapter, which is 25 watts, with my board that's programmed to be 100 watts. So the 3307, you could program it. We program it at the factory for different power levels. So this particular device is programmed at the factory with fuse blow because, as you recall, it doesn't have any I2C. So it comes built in state machine based system. It comes built in with fuse blow settings. So so there's a 100-watt version. But I know that this phone advertises that it charges up to 45 watts. So I'm curious about that, right? Because I want to see how much more power this takes. So I've still got my my sniffer here. I've got the phone. I've got my new board, and I just have basically I have a laptop brick here that's giving me a 20 volts, 100-watt laptop brick. It's giving me 100 watts into my input, 20 volts. Real easy to use, by the way. This board is super simple. Even I can use it. So, I highly recommend you try it out. Okay, so we plug in. I'm going to skip the fact that it discovers a 5-amp cable. We went through that before. So it does that. And then the next thing, once it realizes it's got a 5-amp cable, there's an E marker in there. I kept that 5 amp cable there. It advertises its source capabilities, and you can see it's got 1, 2, 3, 4, 5 fixed PDOs. They're all 5 amps. Let's go to 5 amp cable. And each one increments the voltage. You go 5, 9, 12, 15, or 20. And then finally, the sixth option is augmented. So that's PPS. So that's 3.3 volts to 21 volts, 5 amps. So of course, the first thing that the S20 does, the phone, the Samsung S20 does, is it requests position 1, which is this one, 5 volts, 5 amps. And then about 8 seconds later, it changes its mind, just like it did with the travel adapter. And now it's going for the position 6, which is the augmented, which is the programmable power supplies. Does the same thing it did with the TA. It requests 8 volts, but it's requesting 4 amps now. Before, it requested 2.75 amps, because that was all the travel adapter could give it. And now that it knows it can get more from my board's up to 5 amps, it requests 4 amps. So, which is really cool, because now you can see that there's a living and breathing, it's inanimate, but there's a real charging algorithm going on. There's some smarts in the phone that's reacting differently to different chargers, which is part of the intent with USB-C and power delivery. It makes it much more universal, really, and much more powerful. So it keeps incrementing the voltage, still at 4 amps, 8.04, 8.08, 8.12, 8.16. So these little, gradual steps of 40 millivolts. I don't know why, I don't care, but it is what it's doing. And it keeps doing that. And, I just ran out of screen space here. I just didn't want to keep capturing these slides. And again, this is every, 200 milliseconds, 210, somewhere in there. And what happens in yellow is what I've captured in these screenshots with the sniffer for the messaging. So in yellow, it's first started at 5 volts, which is right here. Again, red is voltage, blue is current. And then it steps up to 8 volts. And then it starts ramping up those steps. Every 200 milliseconds, it wants another 40 millivolts. And it keeps ramping up that. And at the same time, it starts with a current of about, well, it asks for 4 amps. But what it sinks initially is roughly 2 amps. And then it starts ramping up the current. Right? So it's ramping it up from roughly 2 amps to 4 amps while requesting a flat 4 amps for total current. So it's ramping the voltage and the current. And you see you kind of converge right around here. And lo and behold, my board issues an alert, which makes sense because we've hit the 4 amp limit. So, yeah, it does an alert just like we did with the travel adapter. And if I zoom into that alert, you can see that before the alert, it was asking for 9.28 volts at 4 amps. And then we issued the alert right here. And then the phone says, okay, I know I got an alert. I'm going to now bump up the voltage to 9.32 volts from 9.28, which is another 40 millivolts. That's similar to what it did with the TA. You'll notice that that happens right here. It has the alert. And then a little while later, it bumps up the current to 4.05 amps, which is different than before. Before, it just changed the voltage. So here you can see it's like an algorithm just behaving differently based on its source. And that makes so much sense. It's almost, it's a lot more robust way of implementing PD. It's great to see because this is the intent of PD, is so you can have an intelligent conversation ongoing through the whole charge, not just in the beginning like with the laptop. So the current hits so now the new limit is 4.05, gives a little bit of headroom over 4 amps, is continually drawing 4 amps, and then you get another alert up here. Meanwhile, it's incrementing the voltage, but now at a much slower ramp, right? It's slowly ramping up that voltage, and it's right around, I don't know, right at this point, we get another, so here it's 9.74 volts, and at this point right here, you get another alert, and then the phone starts to drop less current. It steadily starts drawing less current. You can see, and it's also requesting less voltage. It's starting to step the voltage down. Here it stepped it down to 9.7. Here it stepped it down to 9.56. Yeah. So one thing I captured right here is roughly just before a minute into the charge. And by the way, for all of these experiments, I started with my sink with an empty battery just to see, that's how much power it's going to consume. It's going to pull out of the travel adapter or the power supply. And you can see the peak power right here is 9.6 volts at 4.05 amps, which is 38.88 watts. So it's really close to the 40 watts, 45 watts that we were talking about at the very beginning. And I just want to point out, because we're using the NCV81599 buck boost controller with the external FETs, we can achieve 98.5% efficiency, which is only 583 milliwatts of dissipation for a total of 38.88 watts. So that's world class. I mean, that's what you want. You want to minimize, you want really high efficiency so the phone doesn't heat up. And so it keeps tapering the current down, stepping the voltage down, and then I expand it out to 6 minutes, and you can just see it stepping the voltage down and stepping the current. Now, I personally, we don't really know exactly what's going on inside the Samsung phone. Somebody in Korea, or maybe not in Korea, wrote the algorithm to do what it needs to do. I'm just observing it. And to me, the big takeaway is between PD 2.0 and 3.0 is this very sophisticated algorithm, right? So if you look at 2.0, its granularity is a lot more coarse for voltage and current. Its algorithm is very basic. It's pretty primitive. And its efficiency is medium, right? Still got good efficiency because you can back in, you can change the volt, you can dial in the right voltage, but it's nowhere near like PPS. With PPS, you got that fine voltage and current granularity. It's, you've got 20 millivolt steps for voltage, 50 milliamp steps for current, which is pretty good. You got a really sophisticated algorithm, as I've demonstrated with the 25 watt adapter and then my board working as a 100 watt source. And you got much higher efficiency. So really with PPS, you have a more sophisticated algorithmic relationship between the sink and the source. The sink is a smart master controlling the algorithm, which is the way it should be, right? That makes sense because the sink is the phone. And it's got an octa-core processor with enough computing power to send someone to the moon in 1969 and back. It's a really, really, very smart device. And the source, which is the travel adapter, it's a smart slave. It executes the algorithm generated by the sink. So, this is really cool. This is what PD 3.0 with PPS gives you. So now I want to talk about the ABCs of efficient fast charging with PPS, right? So I'm going to look at a generic lithium-ion battery charging block diagram. On the left, you have the source, and on the right, you have the sink. So basically, on the source side, you've got the full wave bridge rectifier, a primary controller driving a secondary controller with some sort of isolated feedback, and then that drives the US barrel connector or the Type C. If you're using USB, you would have some sort of USB controller here, and that goes through a cable. You're gonna have some IR drop there. You get to the sink device. It could be a drone, could be a laptop, could be a phone, whatever. It could be a smart power tool. And that's a mobile device. And what you're going to have there, assuming there's a battery, is you're going to have a battery charger. So that battery charger is going to put out a voltage that goes back inside a power path FET and then goes back out to the cell. Okay. Meanwhile, that voltage up here before it goes to the power path FET will probably feed a PMIC or some sort of DC to DC to drive some rails to run the system of this portable device. Point being is this voltage here is not a fixed voltage on a battery. If the battery is empty, it's roughly 3 volts, give or take. And if it's full, it's roughly 4.35. So what I want to point out is, how do you do this more efficiently? And the answer is with programmable power supplies. And that's because you really want to control this voltage here to make best use of the efficiency of the charger. So let me take that and look at that in a little more detail. So I'm going to look at so this is the datasheet efficiency plots for one of my chargers, the FAN5451XX. Okay. So basically it's assuming a VBAT of 3.8 volts, which is here. So that's roughly 50% state of charge. With a 3.8 volt battery voltage here and an input at VBus of 5 volts in blue, you can see that the efficiency is just under 95%, which is good. without changing anything, if you change the input to 12 volts, you can see that the efficiency drops to around 90%. So that's almost a 5% difference, which is significant. The point being is, if the voltage at the input is is just above the voltage of the output, you're going to have higher efficiency, as in 5 volts versus 3.8. If you have a big delta between the input and the output, like 12 volts in, 3.8 volts out, you're going to have lower efficiency. So that just speaks to the idea, the notion that you're going to get better efficiency if you can control the voltages throughout your power path. But let's zoom back out again. And these are the ABCs. I'm going to put A here. That's the output of the travel adapter or brick or AC to DC power supply, whatever. That's A. B is the input to the charger. Remember, there's a big IR drop. This could be a 3-foot cable. There's plenty of IR drop here. And C is the battery voltage. So with PPS, the sync MCU, which is here, and request the ideal voltage from the travel adapter brick at A, because remember, if using USB, it's got this CC pin to send those messages we looked at, which is the whole benefit. Back to the travel adapter to set A to maximize the charger efficiency at B. So it can keep dialing in, say, hey, A, give me 5.6, give me 5.7, give me 5.8, now give me 4.9, whatever it is, because to make this voltage ideal relative to this voltage, which is not a moving target, right? It's got a range of 1.3 volts because it could be at empty, it's roughly 3 volts, and at full, it's 4.35 volts. So as the 1S battery voltage rises, it maximizes the efficiency by managing the voltage points and current points at A and B. So that's the whole beauty of PPS, because it does that with great granularity, and that improves the efficiency greatly. And so it's even augmented more if your batteries are 4 in series, because now instead of a 1.3 volt delta between empty and full, now you've got a 5 volt delta between empty and full, because empty is roughly 12 volts and full is roughly 17.4 volts. So even more important, you get this moving target as the voltage is rising. You want to be able to track that rising voltage with B and A. Not to mention the fact that you've got a load here that's asynchronous to all of this. You have no idea if the user is going to start doing things. If start doing things, it's going to take power away from the charger, and that voltage is going to go up here it's not going to go up there. The voltage is going to go down here if this starts taking some of the power. So it's a great way. PPS is a fantastic way to run an algorithm, and the Samsung S20 is a great example of that. And hopefully this presentation is giving you an appreciation for that. So the call to action with this presentation is to target customers looking for a USB-C PD 2.0 or 3.0 source. PPS is perfect, but it doesn't have to be PPS. Use this 3307-81599 reference design. Again, the ordering link is below. Plenty of them available. And this presentation to help sell. It's yours. Or you can reach out to me if you want some help with a customer. I'm happy to do this presentation with your customers. And look for customers who benefit from a state machine-based PD source. Not every customer cares. A lot of customers have plenty of firmware engineers and they could do this. That's fine. It's still no harm. They could use this as well. But those long-tail customers, and I've worked with them, the customers that have never worked with USB before. So remember, the USB spec, there's 3 specs. There's the Type-C spec, which is over 500 pages. There's the power delivery spec, which is like over 300 pages. And then there's the USB spec, which is over 600 pages. That's a lot of information to get right. So you don't have to worry about any of that by going with a state machine-based solution. It's also faster to market. Plug it in, you start doing things on day one. No firmware development required, and it's also tamper-proof because there's no coding. And we're going to have an automotive version released very soon in 2021. So that's also a nice thing too, because automotive is huge for Type-C. There's going to be, every car is going to have it. At least, my guess is 2 to 4 Type-C connectors. Finally, some customers still prefer an MCU-based solution, so we're releasing 2 MCU-based solutions. this year. The first one in July of 2021 is going to be our FUSB 15200. It's a dual port USB PD dual roll power controller with an MCU. And so that's an ARM Cortex M0 with 128 kilobyte of flash. And so it's got 4 I2C master slave buses, so it can control multiple data sources, as well as power sources. So it can be a sink, it can be a source, and it can also provide data flowing in and out. So this is very good for docks, notebooks and desktops, but docks is a big application. It's a 40-pin QFN, 5x5 millimeter. And what's really nice is it's fully programmable and upgradable open source firmware. And we provide an API for customers to allow them to write their own policy manager development. So that's a nice add-on as well. Or we have a smaller version, which is a 24-pin QFN, which is a 4x4. And this is strictly for being a source. So it's got a dual port USB PD source controller. So it uses I2C to control buck boost and can do the PD on either port. So 2 really nice options, and that's going to be available in Q2 of May of 2020. And that's also the same ARM Core M0. So thank you very much for taking the time to take time to spend with me, and hopefully you see some interest with this this application, this product. I kind of went narrow with this. We have lots of other USB products, but I wanted to really focus in on the charging. I use the Samsung S20 and the MacBook as real world examples. So I hope you see that this is really a really big advantage for working with your customers, is you can show them it really works. You know, it's pretty cool that it just works right out of the box. And it actually, it's keeping up with the #1 5G smartphone in the market. So thank you very much for joining me.